Let us now look at some components which are used in optical communication system. This is the optical transmitter and receiver set by Alcatel. So, this is the integrated chip which has a pigtail fiber and is connectorized on the other side. So, this is chip which is meant for SDS transmission. The chip can be mounted on a PCB like any other chip. This is the pigtail fiber, and the other side of the fiber you have a connector. Similarly, we have a receiver chip, this is again by Alcatel for the SDS transmission. And has similar pins which can be mounted on a PCB. So, the light comes in from the optical fiber and you can get the SDA data out from this chip. So, a combination of these two essentially is the primary requirement for an optical communication link. Here is another device, is the optical switch module which is 4x4. So, you are having 4 inputs which are connectorized here. So, you see these 4 connectors and there are 4 outputs, and by giving control signals the light can be switched from any input to any output. So, you are having here the input which are given by A, B, C, D, and the outputs are 1, 2, 3, 4. So, essentially you are having a cross connect switch. So, by giving different control signals the light can be connected from any of the inputs to any of the outputs. So, this device can be used for creating cross connects or for routing the light on the optical networks. This is the device which is optical fiber couplers. As we know, in optical communication we require devices to couple lights. It could be either erbium doped fiber amplifier or for many other applications. So, these couplers are star couplers, and light coming from any of the input fiber is equally distributed on all the output fibers. So, in a passive area network where light has to be distributed, these optical couplers, the star couplers, are used. This is another device which is a tunable band pass optical filter. So, you see here there is a small knob. When this knob is turned, the tuning frequency of the filter changes. So, if you are getting a broadband light, then a selective wavelength can be chosen by tuning this knob, and this filter works in a wavelength band of 1530 nanometer to 1560 nanometer. Let us conduct now an experiment with tunable laser. So, this is a tunable laser whose wavelength can be changed by turning this knob, and to study the characteristic we require the optical spectrum analyzer, which is this. As you can see, the laser output is connected to the optical spectrum analyzer through this optical fiber. The system is initializing now. These are different settings on the tunable laser. This is the display for the optical spectrum analyzer. We have set the wavelength range from 1530 nanometer to 1560 nanometer. We can start the experiment. It is now acquiring data. The data has been acquired. And that's the display which you get. The x-axis is in nanometers and the vertical axis gives the power in dBm. There is a small window here which shows which is the display window. So, this is the display window, and you can move this display window so that the required wavelength region comes within the window. So, now we have aligned the window around this wavelength. So, you can see there is a noise, and you are having a very narrow wavelength signal which is given by this sharp peak here, which is at 1570 nanometer. These are the cursors you can place at any location you like, and these are the corresponding readings. for the three cursors. So this is the wavelength and this is the power corresponding to that cursor location. So you see at this wavelength 1569.98, which is approximately 1570 nanometers, you have a power in terms of dBm, which is minus 21 dBm. Whereas if you go to other two locations, 1560, which is somewhere here, this is the cursor, the power is 20 dB down. And you can see here that a tunable laser is emitting a wavelength at the moment, which is 1570 nanometers. And that's what is shown here as a narrow spectral line at the spectrum analyzer. Let us change the wavelength now. So by turning the knob, now the tunable wavelength is changing. So let us say we have now set the wavelength, which is 1557.69 nanometer. Again, we can go through the data acquisition mode. Let us put the wavelength 1550 nanometers. The data is getting acquired. One can again bring the wavelength range of interest at the center by moving this window. The different cursors are moved at different locations. Let us look at the close-up of the spectrum analyzer. You can see thus let us now work in storage mode for the spectrum analyzer. Change different wavelengths from the tunable laser and see the display on the spectrum analyzer, which is storage mode display. So you see the first line is at 1540 nanometers, which has come here. You can change the wavelength to 1550 nanometers. Again, acquire the data. You got second line, which is now at 1550 nanometers. The laser is tuned to 1560 nanometer now. Look at the line which has come here. This corresponds to 1560 nanometers. One more reading with 1570 nanometers. Now it is not in storage mode, so only 1570 nanometers is recorded here, which is this line. So one can see here that this device works almost like an oscillator, which we use in laboratories. By turning the knob, the wavelength of the light can be changed. So we are changing here the wavelength of the tunable laser in steps of 5 nanometers. So we started with 1540, 1545, 1550, 1555, here we are seeing the EDFA spectrum, and you are having this line which is coming from the tunable laser. So now we have put this tunable laser in the ASE mode.
Here the demonstration of optical spectrum analyzer is being shown. This shows the screen of an optical spectrum analyzer used to display the signals of an experiment of optical code division multiplexing. In the experiment you will see various components, optical gratings, connectors, broadband spectrum, a setup used to demonstrate the experiment. The demonstration of optical spectrum analyzer. The screen shows the startup. As this has a multiple modules, one of the module which shows optical spectrum analyzer is IQS manager. Pick up the pin and double click on the screen which shows IQS manager. This will initialize the optical spectrum analyzer. Optical patch cord is being connected to input of the spectrum analyzer. Patch cord consists of a notch which has to be matched with the input, which will be demonstrated clearly in the latter part. Has to be twisted properly till it properly gets fixed to the input. The green light on the screen shows the initialization of a spectrum analyzer. This is a clear vision of an input of a spectrum analyzer. At the right hand side shows a notch which has to be matched with the notch of a patch cord, which only gets then perfectly fit to the input after twisting. The patch cord is of FCPC type. This is a screen of a spectrum analyzer. Trace 1 shows a signal 1, trace 2, trace 3, trace 4, 2, 3, 4 signals. Repeating the experiment to demonstrate the startup of an IQS Manager spectrum analyzer with a close view. After double clicking, it shows initialization and the screen comes up with trace 1 shown in green signal, showing the signal of a trace 1. A calibration process is going on and the screen starts, ensuring that the spectrum is ready to start scanning the signal to be displayed on trace 1. The displaying takes place by averaging a multiple signals. The red colors are the markers which come on the screen for a various measurements where there is a change in a power level. Based on the requirement, these can be used for the measurement purpose for the values which are shown in a table of various example as a peak 1, etc. Stop signal will block the signal and the measurement is finished for displaying. Now the optical source is switched on and the start process is continued. The screen shows the scan in progress, where spectrum analyzer is internally calibrating multiple scans and then displaying the average value. Initially, a variation in the peaks shows that the calibration or the measurement has not been fully completed. Now you can see both the peak, all the 4 peaks are of more or less same values. Still the scanning is continued as the calibration is not of a single reading but a display of an average of multiple readings. The display can be zoomed by pressing a lens. A horizontal and vertical arrow shows the windows can be focused as per shown on the screen. You can go to the display where the 4 peaks of a power are clearly shown or more focused, zoomed in. The process shown here is to zoom properly so that the required peaks on the spectrum analyzer are clearly shown. Number 21, 22, 23, 24 shows the markers and respective readings on the screen display. The experiment is for optical CDMA. The 4 peaks shows the encoded part of the signal A. A, B, C is a combination of markers which is required sometimes to mark a specific level on a screen or for the measurement. C is being pulled to be on a peak at 24, which gives the reading as can be seen as 1557.802 nanometers. Similarly, B and A can be placed and the wavelength and power with respect to B and C are displayed on the screen. Here you can see the readings in nanometers on x-axis for A, B and C, and power in dBm for the markers placed on the screen for various peaks 21, 23 and 24. If we want to further zoom, the process is shown, but then the sensitivity becomes a bit higher. The process shows how to perfectly put the readings on the screen so that a proper or correct and exact measurements are taken. On the screen you can see the measurements in power, wavelength for various markers 21, 22, 23 and 24. These readings can be stored by clicking on Quick Save. Write the file name. A default file name is .osw. As an example, consider that we are storing this file as a test file. Say OK, and the file is saved in a channel directory. This is for trace 1. Now let us go to trace 2. This shows that simultaneously I can have 3 readings on the screen. 3 to 4 readings on the screen. There are various controls on X and Y axis. Shows the test mode, normal and drift mode, a wavelength range from custom, full, S band, E band, O band, C band, C plus L band and L band. Or you can also customize the range so as to get a clear resolution of the signals. And this is a power band which can be varied from 154 or 15 dB to minus 45 dB. This is a setting for the measurements. Trace 2. Experimental setup has been changed and new set of readings is being taken. Start is clicked. The process of scanning takes place. The display shows the readings of second experimental setup. A second reading in the same experiment. Placing the windows properly to get a clear resolution. Similarly, I can have different readings on test 3. You can also terminate the scanning process and display by clicking on a stop button there. Now the signal on trace 3 is displayed. There is a provision of comparing the signals of trace 1, trace 2, trace 3 and trace 4 for comparison purpose. This is a trace 2 signal. I can compare the trace 1 signal and trace 2 signals on clicking on select trace 1 and 2. So red color shows the trace 1, black color shows the trace 2, which is a noise, and the comparison of the both is shown. ABC markers are again can be used to mark the particular positions on a signal on x-axis or y-axis. I can recall the signals which are already stored in a previous experiment on trace 2, trace 3, trace 4. As an example, here I am recalling a signal which has been already stored in my previous experiment. The signal in a green color shows of a trace 2, a signal recalled from a output of a optical transmitter. Trace 3 again I am getting different files, a spectral response of 4 gratings connected in series. Similarly for trace 4. Now I have 4 different signals on trace 1, trace 2, trace 3 and trace 4. I can compare any two. This shows the comparison of trace 1 signal and trace 2 signal, trace 1 and trace 3 signals. The difference in the level shows a loss in a connector that is being used. Here the signal is from the optical transmitter. A 0 dBm transmitter is used for an experimental setup. As this is a directly output from a transmitter, the power level is high. Placing the marker on the peak of the output of an optical transmitter, various setups are there. A general channels display setup which has you can display in power in dBm or watts, x-axis in nanometers or terahertz. Background can be shown as a green grid, background grid, x-axis, y-axis, text, various traces, result traces, etc. Channel markers, and you can take a print of the display of a screen edge. Exit the setup. This experiment shows the display of output of an erbium doped fiber amplifier on a spectrum analyzer. Shows the spectrum analyzer. The output shows when the erbium doped fiber amplifier is not switched on. So a noise signal is present. Experiment shows connecting the output of EDFA to the spectrum analyzer. Two connectors, two patch cords connected by a coupler. FCPC couplers are there. When the EDFA is switched on, the screen shows the spectrum of an EDFA. The markers A and BC shows the spectrum range of an EDFA. The green light on EDFA shows the EDFA is switched on. Outputs of an EDFA and input to the spectrum analyzer both are FCPC connections. The spectral profile is as expected of an EDFA on the screen. Which can be zoomed to get a clearer resolution. The spectrum starts from 1519.337 nanometers to 1567.1998 nanometer. The component shows a gratings used for an optical CDMA experimental setup. The series of gratings are connected to form an optical coded signal. A green color connection shows the APC connection. This is an optical fiber coupler which splits or combine 1:4 optical power. A single input and 4 output or vice versa. This is a JDS Uniphase broadband source. Output is FCPC. Output of this is given to a series of grating which will give an encoded output for an experiment. This shows the demonstration and diagram of a spectrally coded optical CDMA system. It consists of user 1, user 2, user 3, user 4, etc. up to user 7. Each user consists of a broadband source, an optical circulator, and a series of gratings connected to circulators to get the output of a grating. Signals are combined by a combiner, power combiner. A splitter is used to equally distribute the signal power between decoding gratings A and decoding complementary gratings A. Output of this are connected to photodetector 1 and photodetector 2. This shows the wavelengths used for lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, lambda 7. In optical CDMA, simultaneously 4 signals are transmitted for a M sequence code of length 7. So codes are selected such that based upon the codes assigned to each user. So for an example, user 1, the signal is coded with lambda 1 signal, lambda 3 signal, lambda 4 signal and lambda 5 signal. User 3 is encoded with lambda 3 signal, lambda 5 signal, lambda 6 signal and lambda 7. Each wavelength lambda 1, lambda 2 or lambda 7 can be obtained by connecting a broadband source to a series of respective gratings which are reflected, and the output is taken through optical circulators. So for a system with code length of 7, the table gives the signal encoded for user 1 to user 7. Lambda 1 value 1531.95, lambda 2 1538.23 are such that they are from a ITU grid and not randomly taken. So encoding of this signal is done and decoding is done with respect to the principles of a spectrally coded optical CDMA system.